Good day to all of you. Today we shall continue with the discussion on modeling of DC-DC converter. Till now we have seen how we can obtain the state space representation of any given circuit. We have seen a first order system in the previous class. We shall continue from there, take up a second order system and then specifically take up the case of a DC-DC converter. Now, if you see, the example of a circuit that we had taken in the last class, the RC circuit, and to this RC circuit we now introduce another element here called the inductor L. So, the inductor is one more dynamic element. So, if you see, the RC circuit had the R, C and let me call this as R2. Now, one more element, the L, is now added, and at the input let us supply it with a voltage Vg, and we require a voltage at the output which is set at V naught. Probably that is what you would like to control. Now, this circuit at the outset, looking at the number of energy storage elements, we see that we have the capacitor C as one energy storage element, storing energy as half C V square, where V is the voltage across the capacitance, and another energy storage element L, storing energy within it as half L I square by virtue of the current I flowing through the inductor. Now, following the steps that we discussed in the last class, the first step was to identify the energy storage elements, and that was this, and by this we know that this is a circuit of order 2. So, it is a second order system, and therefore, we will have two differential equations that will represent the system. So, if we have such a case like this, order 2, we need to choose now the variables. I will not now list step 1, step 2, step 3. I am going to do it in a continuous manner, but the process will follow the steps as enlisted in the last class. Now, the variable list. So, let us say the input variable U is nothing but Vg, the states. What are the states of the system? States of the system are nothing but the outputs of the integrators, and in this case we have two. One is with respect to the inductor, another with respect to the capacitor. The energy variables with respect to the capacitor being the voltage across the capacitor, V c, and the energy variable with respect to the inductor is the current through the inductor IL. Now, these two are the state variables, and therefore, we can list them here. So, one is IL and the other one is we see the voltage across the capacitance. And the parameters of the system are R1, L, C and R2. So, these are the list of variables that we will be using and restrict ourselves to in arriving at the state space representation of the above circuit. Note that this matrix is called the input vector, and this array is called the state vector. It is self-explanatory because it means that this is a vector or an array which contains state variables. The U vector or the input vector contains an array of input variables. Now, let us go about writing down the equations. First, let us clear the screen by deleting these portions. And write down the equations afresh here. Now, according to our listing, step listings, the next task after having listed down the variables is to start writing down the differential equations, one dynamic variable by dynamic variable. So, starting first, let us say with the inductor L. Now, we know that L dIL by dt should be equal to the voltage across the inductor, should be equal to the voltage across the inductor, and in this case the voltage across the inductor is nothing but this voltage minus this voltage minus this voltage. So, therefore, it is Vg minus Vr1 minus Vc. However, we have to represent only in variables that are permitted, which means state variables and input variables. Vg minus Vr1 can be written as IL into R1 minus Vc, which is already a state variable. So, therefore, segregating, you have dIL by dt, which is equal to minus R1 into IL which is this, divided by L minus 1 by L into V c plus 1 by L into V g, where we have segregated into two distinct parts. This is the part which contains the state variable component, and this is the part which contains the input component. So, this is the first part, differential equation 1. Okay. Now, the second differential equation is the one which is connected with the capacitance C. So, let us clear some space. And write down the differential equations for C. So, you have C dVc by dt equals, now C dVc by dt equals the current through the capacitance. Now, the current through the capacitance at this summing point is the difference between IL and the current that goes into the load R2, and this current which goes into the load R2 is nothing but V c state variable by R2. So, therefore, this is nothing but IL, a state variable, minus V c by R2. So, this can be written down as follows. dVc by dt, which is equal to 1 by C IL minus 1 by R2 C into V c plus 0 V g. So, there is no component of the input in this particular equation. Both are state components. The capacitor value C is taken to this part, this side of the equation, rearranged to obtain these coefficients. Now, these are the two equations which have been developed from the two dynamic components. And these basically form the state equation if they are rearranged in a proper manner. So, let us do the rearrangement by copying this equation set into a fresh page. Now, this equation set, we will arrange it in the form of a matrix. So, IL dot would imply di by dt, Vc dot would imply dVc by dt, Now, we represent this portion in the following manner. We have a matrix, we call that the A matrix, and that A matrix is multiplied by the state vector, and this is nothing but the state vector derivative. So, what should be the state vector? We have already defined the state vector, which are the energy variables here, I L and V C. So, correspondingly, we can fill in the elements of this matrix by looking at the two set of differential equations, as we have written above. So, the coefficient of I L, we write it down, R 1 by L. Now, the coefficient of V C into its corresponding place, again the coefficient of I L with respect to the second equation, and so on. So, this matrix, square matrix, forms the state parametric or the characteristic matrix, which actually defines the system using the parameters of the system. Plus, still it is not complete, we need to address this part, the input part. So, we make a placeholder for these two matrices. One is called the B matrix, another is called the U matrix, which is the input. So, this is nothing but V G, and then looking at these two values, we populate the B matrix as follows. So, notice that this equation is in the form x dot equals A x plus B U, and this is nothing but the state equation. For the second order system or second order circuit as shown here, RLC circuit. Now, if you observe this equation, this vector, the x dot vector, provides the derivative or predict the slope at that current point of time, and which gives the possible extrapolation for the next or the future point of time. This is actually a prediction, how the state will evolve in future. That is what this would give. This matrix gives the property of the circuit in terms of its component values, and the state vector I L and V C are nothing but the energy variable, as I have already stated, plus the input scaling matrix and the input itself. Okay. Now, this state equation as a whole would give you the dynamics or the dynamic relation between the various variables, signals and inputs for the system, for the specific system. The next aspect is to obtain the output matrix. Now, output matrix is of the form Y is equal to C, a scaling matrix, into the state X, state vector, plus D, another scaling matrix, to U, which is the input vector. So, what is supposed to be the output? The output for this specific circuit is V naught. V naught is what we want to be the controlled output. Therefore, we put that down as the output. V naught equals a matrix which scales the state. And what is the state vector? State vector is nothing but IL and VC plus another matrix which scales the input, and input is nothing but VG. Now, we see that there is no direct feed forward from the input to the output. So, D is nothing but 0, and again looking at the circuit, we see that V naught is nothing but the voltage across the capacitance, and therefore, we scale, give the numbers to the C matrix accordingly as 0 and 1. So, directly the capacitor state value, state variable value will be the output in this particular case. So, this equation is called the output equation. The state equation and the output equation together form the state space representation, and always, as I have been telling since the previous class, we represent it in this form. The state equation and the output equation. Even though it may seem a bit repeatable, this is very fundamental and very important part of developing a model for any DC-DC converter. So, this portion has to be understood thoroughly before going on to the next part, which is we try to get a state model, state space representation of a DC-DC converter. So, using this as the basis, we saw how to get the state equation for a first order system. We saw how to get the state equation for a second order system, but both these systems were continuous states, meaning the states did not have any jumps in between. The circuit was a continuous domain circuit, analog circuit, though power analog circuit. Now, the DC-DC converter case, there is a difference. There is a major difference wherein a switch component is introduced. It is not just an R, L and C. Apart from these three, there is one more component which is a nonlinear component, which has two states. Either it is on, the resistance is 0, or it is off, where the resistance tends towards infinity. Now, these two states change the structure of the circuit, and this is where the complication sets in, and we need to appropriately make assumptions to arrive at a state space representation. So, we shall see how we go about doing that. However, we will bank upon these basics of how to obtain the state space equation representation of a circuit, of a general circuit, and use that one appropriately for the DC-DC converter case. Now, let us start by considering the case of a very simple DC-DC converter, and that is the buck converter. To start with, we shall start deriving the model for a buck converter, buck DC-DC converter. You are all familiar with the topology of the buck converter when you have discussed its steady state characteristics, analyzed it, and saw how it behaves, the operating principles. So, basically if you look at the buck converter, it consists of an unregulated source VG or Vin, as whichever symbol is convenient to you, you may use that. There is one switch and another in a fashion as shown here, followed by an inductor and C filter, LC filter, which is the averaging network, and of course, the load R, C, L, switch 1, switch 2. Notice that maybe earlier you probably may be familiar with this form, that is, you have two throws in the case of a single pole double throw switch like this. So, this is a representation that one would start with a single pole double throw switch, where the switch pole is placed at throw 1 for a period of time dt and placed at throw 2 for a period of time 1 minus dt. This t and this t are different. Now, the single pole double throw switch is represented as two single pole single throw switch. This is a SPST switch. This is a SPDT switch. Okay. Both are exactly equivalent. However, while implementing, you are implementing normally with two separate switches, wherein S1 is replaced by probably a semiconductor switch like a transistor or a MOSFET or an IGBT like this, and S2 is replaced by a device like this, a diode. Okay. So, you start with a single pole double throw switch, and then as you progress, you switch over to single pole single throw switches, and then replace the single pole single throw switches with the semiconductor switch symbols to go more towards the implementational circuit. Yeah, for now, let us erase this portion of the circuit. And see in what manner we can model this DC-DC converter circuit. Now, I have shown two arrows here. Basically, what it means is that there are two distinct time periods within a period. dt is a period. Now, if I indicate time axis as t here, and if I indicate here that this is the time t, time period, total switching time period t, and this is split into two parts, wherein this part we call it as dt, d is less than 1, the duty ratio, d is duty ratio, and this part is 1 minus d t. So, during the dt part, the switch S1 is on and switch S2 is off. So, let me indicate during the period dt, S1 is on, S2 is off, and during the period 1 minus dt, S1 is off, S2 is on. So, these are the two possible modes of the circuit. So, during dt, what happens to the circuit? How does it look like? So, during this period, you have the supply Vg, the switch S1 is on, and drives directly through the inductor, capacitor, resistor, in this fashion, and I am going to show the dotted switch S2, which is not used. So, it is essentially out of picture, it is not there in the circuit. During the time 1 minus dt, the switch S2 is on and S1 is off. So, which means that the supply, which I am going to show dotted now, is out of picture, and as switch S1 is open, it removes that portion out of the circuit, and we have S2 on as shown here, and the inductor and the capacitor, which contain energy by virtue of the voltage across them and the current through them, and the inductor energy will freewheel through the switch S2. So, this is how the circuit would look like when the switch S2 is on and S1 off. Now, you have these two circuits and we need to model them. So, we take the approach that we write down the state equation for this mode of operation of the circuit. Then we write down the state equation for this mode of operation of the circuit, and then we combine the two to arrive at some kind of an averaged state space model for that portion. So, we shall do just that, but before that let us copy this portion of the circuit and take it on to a fresh page, and develop the model for these two. Now, here we will have a vertical split. This is the mode of operation during dt period, and this is the mode of operation during 1 minus dt period. By inspection, of course, step 1 of your modeling procedure, we have two energy storage components, L and C, either of the modes. So, you will have order 2 in this mode, you have an order 2 in this mode, 2 differential equations in this mode, 2 differential equations in this mode, and then we make the combination. Identification of the variables. Vg is one of the variables, input variable. Vc across the capacitance is another variable. IL through the inductor is another variable. Likewise, in mode 2, Vc across the capacitance, which is same as output voltage, and the current through the inductor. These are the two state variables. Vg of course is 0 here, it is not connected, but anyway we shall write in the variable. And then the list of parameters, you have L, C, R, you have L, C and R in both the cases. Now, we are ready to write down the equations. So, mode by mode, first mode during the mode dt, let us write down the equations. Two equations which are L dIL by dt, which is equal to the voltage across the inductor. The voltage at this point is nothing but Vg, and the voltage at this point is nothing but Vc. So, the voltage across the inductor is nothing but Vg minus Vc. Then the next equation dVc by dt, we will do the simplification later. The capacitor equation, differential equation C dVc by dt is nothing but the current through the capacitance, which is the current through the inductor minus the current flowing through the load resistance R. So, therefore, we can write it down as IL minus Vc by R. Always use just only those variables which we list down, which is the state variables, input variables and the parameters, nothing else, nothing more. Now, these are the two equations in mode dt when the switch S1 is on. Likewise, the two equations in mode 1 minus dt when switch S2 is on, S1 is off. So, you see that L dIL by dt is equal to the voltage, and at this side of the inductor is 0 as it is shorted to the ground by switch S2, voltage on this side is VC. So, you write it down 0 minus VC, and the capacitance equation C dVc by dt equals current IL through the inductor minus the current which flows through the load resistor R. So, we now have two equations each. We now put them in the state space representation. Each of these sets of equation you can put it in the state space representation as follows. You have IL dot VC dot. They represent the derivatives of the state vector, nothing but x dot. Now, you have a matrix, the state vector x plus the B matrix state vector u. Sorry, the input vector u, and the input vector is nothing but Vg. Now, we just fill in the elements of the matrix. Look at the equation here. IL, the coefficient for IL in this equation, in the first equation here, is 0. So, we put in 0 here. The coefficient of Vc is minus 1 by L by taking L onto this part of the equation. Likewise, for the second equation, the coefficient of IL is 1 by C by taking the C into this side minus 1 by R C. So, this forms the A matrix. The B matrix, again looking back into the two equations, you have the coefficient of Vg, which is 1 by L. So, some amount of steps I am skipping, doing it mentally, but you need not actually skip these steps, you can write them down, but with experience I think you can do things faster. And the second equation, you see that there is no Vg term in this second equation, and therefore, this becomes 0. So, this becomes the state equation for that part of the circuit, or that segment of the circuit which is operative in mode where the duty cycle is dt, the time period is dt. Likewise, similarly, for the mode where the period of operation 1 minus dt, we write down the state equation in a similar manner. You have IL dot, the derivative, Vc dot, the derivatives, nothing but x dot, that is equal to, we have a state characteristic matrix multiplied by the state vector x. So, therefore, this has to be A plus the input scaling matrix B and the input itself Vg. u in this case. So, you can observe here that the first line of the equation, there is no IL component and therefore, the coefficient of IL is 0 and we populate the coefficient of Vc 0 minus 1 by L by taking L onto this side of the equation, and looking at equation 2, coefficient of IL is 1 by C by taking C onto this side, coefficient of Vc is minus 1 by Rc. So, that we write down 1 by C minus 1 by Rc. So, this forms the A matrix, and in the case the B matrix, there is no input term coming into the picture here, both are 0. So, this forms the state equation for these two modes. And we are going to call it x dot, because the state is same, renaming it as A1 x plus B1 u, and then we will use x dot equals A2 x plus B2 u, just to indicate that this is one state equation and this is the other state equation, and we need to combine these two in some form, some manner, some kind of an averaging we need to do. Likewise, in a similar manner, the output equation, very simple, is nothing but V naught is our output and V naught is nothing but V c, and therefore, the C matrix is nothing but 0, 1. I think we shall use a fresh page for this purpose. Let me write in the line of demarcation. Okay. The output is of the form y is equal to C 1 x plus D 1 u, and in the second case output, same output is C 2 x plus D 2 u. So, V naught is the output, and we know that the state is state vector nothing but IL and Vc. We need to populate the C matrix, plus we know that there is no input term directly connected to the output. So, we may as well not use it. So, that is 0. And here too we have V naught, which is equal to the C matrix and the state IL Vc. So, this is nothing but 0 and 1, because Vc is directly coming to the output. 0 and 1 both are same, but still we denote it by these two output equations. Now, how do we combine these two into a single common model? Now, this equation, this set of equation during the period dt and the set of equation during the period 1 minus dt are called the large signal models. A1x plus B1u x dot is equal to A2x plus B2u, y equals C1x plus D1u, y equals C2x plus D2u. So, these are called the large signal model during dt period of time, and this is the large signal model during 1 minus d t. So, what we now do is combine these two by averaging. Take this model, average it by multiplying by d, take this model, average it by multiplying by 1 minus d, so that we get some kind of a state averaging. So, if I take for example state x here, x into d that is x during time dt plus x during time 1 minus dt into 1 minus d would give you some kind of an average state x average. So, this kind of an averaging is done. This is actually an approximate. What basically happens is that the state lose some information. For example, if I take the simple case of an inductor current, the inductor current in the case of the buck converter is like this. Let me put the time axis t. This is time period dt 1 minus dt. This whole is time period t. Again dt 1 minus dt, so on it proceeds. Now, how does the inductor current IL look like? Period to period. So, you will see that there is a rise portion. This you have studied during the, when you are studying discussing the operation of the circuit. So, it rises with a slope of Vg minus Vc by L, falls with the slope of Vc by L, again rises, falls, so on. Now, if you take one period, if that period is very small enough compared to the time constants involved, LC time, LR and RC time constants involved, then we could say that the average value of the state, this is actually a state IL. So, the average value of the state, instead of writing it like this, if you say this is the average, this is the average of this state, and during this period, this is the average of the state during this period, so on. Then we call this as the averaging of the large signal. So, how do we achieve the averaging of the large signal? We take the state value here, multiply it with D. So, let us say if this is IL during D t period, and if this is IL during 1 minus D t period, then what do? We said IL average equals IL during dt period into d t plus IL during 1 minus dt period into 1 minus d t divided by the time period, which is the whole t. So, therefore, we obtain IL dt into d, IL of the state into 1 minus d. That would become the average value of the state during one time period t, and that is this value. So, this is the approximation that we do, assuming that the time period is small. So, which would imply that if I have the inductor current dynamically changing with respect to time IL, if it proceeds in this fashion and then comes to some kind of like this. So, we are making the approximation saying that we have an average like that, an average like that, average value like that, so on for every time interval. So, this red marked curve still indicating the dynamic, but the time period being very small compared to the dynamics of the system, this is called the averaged state, and we call it as the averaged large signal, where this is the blue is actually the large signal under consideration. This is the large signal under consideration. Thus, any state, if we take, the averaged value is nothing but x, the state during the period d. I am indicating now small d. We will explain why small d later on. During the period d into d plus x during the period 1 minus d into 1 minus d. This would become the averaged state within a period, and this is called the averaged large signal state model. Okay. So, from these two models, what we do is obtain a new state representation x dot, which is equal to a x plus b u, where each corresponds to the averaged value called the averaged large signal model. We shall continue with this obtaining the averaged large signal model from the two large signal models, which is x dot is equal to A1x plus B1u and x dot is equal to A2x plus B2u. Now, these two models will be combined together in this fashion by weighting it with d and 1 minus d. And instead of uppercase d and uppercase 1 minus d, we will be using in future d lowercase 1 minus d lowercase. The logic and the reason for that symbol change will be explained in the next class. Thank you for now.